Hey guys, welcome back to my channel, and today we're gonna solve one of the problems of concrete design. We choose national examinations of May 2018, and let's start with a problem. Let's do the problem B3 here. So I'm just gonna read this problem real briefly, and we're gonna proceed. So what we have is overhanging reinforced concrete beam loaded as shown in the figure B3, and we need to determine the dimensions of its rectangular cross section and the steel reinforcement to satisfy moment and shear. We also need to take into account the self weight of the beam, and we got a compression strength of concrete as 35 megapascal and the yield strength of steel as 400 megapascal. And we also have in this problem, they give us a drawing that shows us the 50 kilonewton per meter distributed load as on this beam, and the span on this beam is 6 meters. Alright, let's do this. Okay, so we have the compression strength of concrete as 35 megapascal and the yield strength of steel as 400 megapascal. And I'm just gonna quickly draw this beam here. Not gonna really worry about making it as perfect, but just gonna quickly draw it here. It's gonna support A or support B. This is 1 meter, 4 meters, 1 meter, and we got a evenly distributed load. And I'm not gonna mark it 50 kilonewton per square per meter yet, because we're gonna have to apply the loading case for this beam, and our actual loading is gonna be more than what's given, because we have to factor it by the loading case. And before we do that, we have to make an assumption of the cross section for this beam. And as it said in the problem, they're asking us to design a rectangular cross section. So what we're gonna have to do, we're gonna have to assume a rectangular cross section for the beam, and the easiest way to do it is assume as H would be span over 16. So what we're gonna have is 6,000 over 16. We're gonna get 375 millimeters. So this 375 millimeters, that's your basic minimum, let's say, what you want to do for when you start designing the cross section. You don't want to go really below 375, but in most cases it's safe to save. For example, solving these problems, you can go more, bigger section, just to be safe. This way you don't have to recalculate in the next steps, because if you take too small of a section, you can end up having too much reinforcement. Then you have to recalculate it, and you have to do the compression reinforcement as well as tension reinforcement, which will complicate the problem even more. So in this case, we don't want to do that. We want to just have tension reinforcement on the bottom of the beam. So what I'm going to do is I'm going to make an assumption. I'm going to assume the section of 500 by 400 millimeters. See, I went a little bit more, but this will give me enough room that I don't have to do any recalculation at the end. And it's possible to do recalculation if necessary, but really you don't have to do it in an exam, so we're just gonna go the easy way. Then we're gonna have to calculate the weight of the beam, because the problem tells us that we need to include the self weight of the beam, and we need to calculate it into the problem. So we're gonna calculate the dead load. It's gonna be 0.4 times 0.5. That's your meters. We transform millimeters into meters. and then times 24. That's your weight per cubic meter, 24 kilonewton per cubic meter. So, and we end up as 4.8 kilonewton per meter. So altogether, like also we have to do what we have to do next step. We have to apply the load case, and in majority of cases, you're gonna have to use this book again, like I showed you. So we're just gonna go to the loading cases, and these loading cases here, they show us there's 5 loading cases you can choose from. But in the reality, for this exam, you just want to go 1.25 for the dead load and 1.5 for the live, which is so like let's say here, so 1.25 dead and 1.5 live load. If you also have some snow load, you can go 0, just once for the snow, or 0.4 for the wind. But that's just different case. We're not gonna just include it in this video. I'll do another video for explaining more on these loading cases. But in this case, we're just gonna go with the case number 2 for principal loads, 1.25 dead and 1.5 live load. So let's do this. So our total load will be 4.8 times 1.25 plus 50 times 1.5, and then we're gonna end up with 81 kilonewton per meter. So right here we can actually say it's 81 kilonewton meter. I'm not gonna do analysis on this beam. I have already done it before, but if you guys want me to show you how to do that, I can do another video for doing a structural analysis that gonna show you how to properly do the analysis for the beam. So if you're interested, just give me just write it in the comments below, and I'll try to do it as soon as possible here, and then show you how it's done. So yeah, I'm just gonna draw this here. So this is gonna be our shear force diagram. And this is going to be our bending moment diagram. So this is our BMD and this is our SFD. So okay, and what I got here, this support reactions, I have 243 kilonewton on each support. So the maximum bending moment we've got is in this point right here, and it is 121.8 kilonewton meter. The negative moment is only 40.5, which is way smaller than our positive moment, so we're not gonna really worry about the negative moment that much. And for the shear force, we have 162 kilonewton here and minus 162 here. So our maximum moment, bending moment, is going to be 121.8 kilonewton meter, and our maximum shear is going to be 162 kilonewton. So these are going to be the values that we're going to want to design our beam for, and our beam should be able to withstand this these values. Okay, so let's do this here. Just gonna start another page here. Okay, so now we know that we got the beam 500 by 400 millimeters. Next, what we need to do, we need to assume the reinforcement. So basically what we need to do, we need to assume the bar size, we need to assume the stirrup size, and we need to assume the concrete cover. There is different sizes of bars available. So in this case we have many different sizes, like starting from the smallest one, 10 m, and ending up with 55 m. And you have the area of each bar for the area in millimeters square, and then diameter of each bar. For this problem, let's choose 30 m, which is going to be 29.9 millimeters in diameter, and it's going to have 700 square millimeters of area. So we go assume 30 millimeters bar. Then you always want to go 10 millimeters stirrups. That's like really more common, unless you have like a really high lots of like the value of shear is really high, then you can go 15 m or even 20 m. But in this case we don't have too much shear force, so we're just gonna go 10 m stirrups. And we'll go 30 millimeter concrete cover. Usually go 30 millimeter concrete cover for the buildings, for the beams that are located inside the structure, inside the beam, that are not exposed to any corrosion or environmental weather and stuff. So you just go with a 30 millimeter. Then we need to calculate the depths of the steel reinforcement, which is called D. And D is gonna be, we get our height of the beam, which is 500. Then we have to minus 30. That's going to be our concrete cover. Then we go minus 11.3. 11.3 is the diameter of the stirrup. It's given in the book. And then we go minus half of the diameter of the 30 m bar, which is 29.9. We go half, so we end up with 443 and 75 millimeters. Next step, what we want to do is we want to find the ratio, how much percentage of steel reinforcement we need to have in the beam to satisfy for the bending moment applied to this beam. And in this case, this handbook gives us a really easy solution how to do that. And there is another way you can do it. You can also do it through the structural analysis. It's a little bit different. It's not much harder, but I mean, you can do it quicker this way if you only have to do for the tension reinforcement. So I'm going to show you this easy way. What you're going to have to do is you go to the table 2.1, which gives you here, it gives you all the percentages for the singly reinforced beam, for the tension reinforcement, and for different strengths of concrete. And you can only use it though if you have the yield strength of steel as 400 megapascal. If you have something different, if you have 350 or 300 megapascal, you cannot use this table. You have to use the structural analysis to calculate for the reinforcement. So first what we want to do is we're going to use this formula. We got to find KR, and KR is going to be MR times 10 to the power 6 over B times D squared. So we're getting RMR was found here. We get 121.8. So 121.8 times to 10 power 6 over B was 400. So we get 400 millimeter times D. We calculated D here, so it's 443.75. And we're gonna get 1.54. So this is gonna be our KR. And then we go to this book here, and we find the compression strength of concrete is 35, and then we're gonna have to find KR. So you see like the KRs here, so you're gonna have to find 1.5. This is gonna be 1.5. Then you go here and you get the ratio, the percentage of the steel reinforcement, 0.46, and then you go here 1.6, and you go and you find the raw as 0.49, and you just have to interpolate between these two numbers. I'm gonna show you how to do that real quick here. So you just go from table 2.1. In the exam, you always have to write down where you get these numbers from, so that's not like they came out from just from your assumption. If you assume something, you just write assume, right? Then it's clear that you assumed it. It's not a statement that's written in stone. So yeah, just go right from table, and then you can write KR 1.5, and then we got this raw as 0.46. Then we write KR 1.6, and then we got this raw as 0.49, and then we get the KR, which we have here, 1.54. So between these two, we're gonna find the raw. I have done the interpolation already, so it's gonna be 0.472. Again, if you want me to do the interpolation later on, just write in the comments below. I'll show you how to do that, but I'm pretty sure you guys know how to do that. But if you have any questions, or you want me to see how I'm doing it, just write it down, and I'll be happy to show you. Okay, so this way we found the raw, which is the percentage of steel we need to have in this beam. And what we need to find next, we need to find the area of the steel reinforcement that we need to have, which is going to be AS. This is our area of steel, which is equal to raw BD. And again, this one, it's all these formulas, they are in the book, so we're not making them up. So we go this way, so we go 0.472, and since it's percents, we have to divide it by 100, then multiply by B is 400 times 443.75, and we get 837.8 millimeters square. So since we got 837.8 millimeters square, what we have to do, we have to go divide them by the square area of one bar. And since we choose this 30 M bar, we're gonna divide it by 700, because area of each bar is 700 millimeters square. So we're gonna end up with 1.2 bars. Since we cannot take 1.2 bars, we have to take 2 bars. So we'll just put approximate sign, we'll take 2 bars. In this case, like if I would have taken smaller diameter bar, I would probably end up with a little bit higher area here, and then when I would divide it by smaller area per each bar, I would end up with 2-3 bars, or maybe 4 bars, depends what size I'm taking. It doesn't really matter, like when you do an exam, as long as you do it the right way, it's not going to really matter, because on the exam you only get like 35 minutes to solve the problem, so you're going to have to time yourself, like to do this problem in time. And you can always make a note at the end that revision could be held if necessary, and find for different size of the beam and different assume different reinforcement. Okay, so anyway, we get 2 bars. So we get 2 bars, and each bar is 700 millimeters. So we end up with 1400 millimeters square of steel reinforcement. Okay. So now, basically, we have already designed the beam. We already got the cross section that will satisfy the bending moment. So for the bending moment, we basically designed the beam already. We have the steel reinforcement for the bending moment, and we have the cross section. But you want to double check and make sure there is few checks you have to do on this problem to make sure that you designed it right. So in this book, you can also have you got a formula for the minimum steel reinforcement for a concrete beam, which is this one. As you can see, this is going to be a formula for the minimum reinforcement. That's what we're going to check right now. So we go AS min 0.2 square root of FC FY B TH. So we go O2 times square root of 35 compression strength of concrete divided by yield strength of steel times the BT is the width of the tension zone. So make sure it's, if for example you design in a T section, you're gonna include the width of the tension zone. And it was 400 times H is our 500. And we end up with 591.6 millimeters square. So since 591 millimeters square is less than 1400 that we got, we satisfied this requirement, and this check is passed. The second check you want to do is spacing. You want to make sure that you have enough width that when you put those bars in the beam, you're going to have enough room for the concrete to flow, because concrete is not just liquid, it has fractions, like the aggregate fractures that have like different diameter, and you want to make sure you have enough room so those rocks that are included in the concrete, they're gonna freely flow between those bars, and there is not going to be any air in the concrete beam, because you don't want to have any spaces or air spots or pockets in the beam once it's cured, right? So yeah, we're gonna do that now. So this is gonna be our first check. The second check is gonna be spacing. So we go spacing, we go with a 400 millimeter, that's the width of the beam, minus 30 times 2, that's gonna be our concrete cover on both sides, minus 11.3, that's gonna be our stirrup times 2, minus 29.9, that's the diameter of our steel bars, times 2. We have 2 bars, right? And then we're gonna have to, yeah, that's it. And we end up with 257.6 millimeters. that's plenty, but the code gives us idea of how much bar spacing you need to have in each one. So here's the code says that the spacing should be bigger than 1.4 of the diameter of the bar, 1.4 of the aggregate size of the rocks that's included in the concrete, like aggregate size of material that's rocks in the concrete, or bigger than 30 millimeters. So let's do this. So our S has to be more than 1.4 times 29.9. We get 41.86 millimeters. So this is okay. Then since the problem doesn't tell us the aggregate size, we just ignore it and don't just count it. So, and then also 30 millimeters. Since spacing is bigger than both of them, this check is done. It's all good. So the last check for this beam is going to be it's called the crack control, and this crack control is also important because depending on how many bars you have, there could be cracks appearing in the concrete. So in the beam, you want to make sure that they're not going to appear because of that. So let's do the third check. It's going to be our crack control. And we go. This is also included in the code. I'm going to show you here. So this is how you calculate. This is actually going to show you way better than I can show you. So this is the formula you're going to have to calculate. And then this is how you calculate. So if you have only one layer of bars, your DC is going to be concrete cover, stirrup size, and then half of the diameter of the bar. And then your area, shaded area, would be Y, and your Y would be the same as the DC. So DC times 2 times the width. You're gonna get the shaded area, and then you divide it by the number of the bars, which we have 2 bars, and then you're gonna get A. So you have DC A, and Fs is taken as 0.6 of Fy, and then we got the formula to calculate that. So let's just do it real quick here. Fs DC. So our Fs is going to be 0.6 times 400, 240 MPa. Then our DC will be 30 plus 11.3 plus 29.9 times divided by 2, which is equal to 56.15. So our A will be 56.15 times 2 times 400 divided by 2. We're gonna get. So we're gonna end up with 22,460, and then in this one, I'm just gonna go 240, 15 times 22,060, and my results show me that we got 25,929, seems like, and then which is going to be less than 30,000 given by the code Newton millimeters. So let's say this is okay. It passed the crack control check, So we can say that this design is satisfying the bending moment for this beam is going to satisfy the bending moment, and it's going to be withstand the bending moment. As well, just it's worth mentioning that if you have a beam with the height over 750 millimeters, you need to do the skin reinforcement check as well. So the fourth check is the skin reinforcement. Only for beams over 750 millimeters high. And the skin reinforcement is gonna be this check right here. So I would suggest in the exam, really, if you can, avoid getting a beam more than 750 millimeters. Of course you can do it, but it's just gonna take way longer and you have to do another check, so might as well stick to the something that's more simple. Okay, so this is how you guys design the basically beam for the bending moment, for singly reinforced, for the tension reinforcement. And we can also draw this beam just to show how it's gonna look. So this is gonna be our 500 millimeters, so 400 millimeters. We got 2 bars, the stirrups. So these 2 bars is going to be 2 30M bars, and these stirrups is going to be 10M. The next step is going to be design for shear, because designing just for the bending moment isn't enough. We're going to have to design it for shear as well. We need to know how much stirrup do we need to put in this beam to withstand the shear. And we know that the shear is causing the cracks on the beam, and so it has to be designed so it can withstand that shear force that's acting on the beam. This is going to be our part 2, because I think this video is already taking a long time. So if you want to watch part 2, it's going to be designed for the shear, and we'll be right back.